basic waveguide demonstration. I feel terrible that you're not able to be here to do this in person, but it's the way it is. So I've intentionally copied the slotted line experiment that I demonstrated last couple weeks ago. What we've got is our microwave sweeper. I've changed out the source. This source can do 5.9 to 12.4 gigahertz. The control unit on this side is the same. I currently have it set at 8.5 gigahertz. I have CW selected, which means continuous wave or just one single sine wave. I've got my square wave modulation on so that I can use my slotted line system, and then I've got a power button over here. Now I'm going to demonstrate that this truly is working, right? So right up here I have a VSWR meter to measure. This is the microwave version of a slotted line. This was the slotted line in coaxial systems, where we had that little center conductor, not so little, in the middle, and this was our probe system, right? So there was our probe that went down in to measure a little bit of the RF signal. I have a similar kind of probe system here. I'm not going to pull it out, but you can see this probe, which is part of the waveguide system, right? Actually, I can pull it out. It's not that big a deal, but it just goes down into the waveguide to measure a little bit of the RF signal. Put it back in there. We're going to use that a little later. So when I turn on the power, you're going to see the meter rise up, right? And that comes from the little bit of sample data. Now I'm going to transmit that data via waveguide, or signal via waveguide. So I've got a waveguide horn here. Now this is where RF in microwave starts to get very different from RF in waveguide, or so in microwaves, right? So this horn, we call it a waveguide horn because it's shaped like a horn. There's different versions of them. Here's another version of it. These happen to be the same frequency. This waveguide horn will allow the microwave energy to come out, and I'm going to bring it over to this waveguide horn, and I'm bringing it through a device here called a directional coupler, and then I have my RF power meter. And here, that's the reading on the RF power meter. You can see it's around minus 17 dBm. If I turn off the power, you'll see that that auto ranges to go minus 41 dBm are basically off. So there, I've turned it back on, and I see the signal there, and I see the signal here. Off, and then back on. So that shows you that we really are transmitting the RF energy. So we're going to take measurements on both ends, right? On the receiving end, there's not much really to make measurements of. I can change the frequency and change the power level, but there's really not much else I can do because it's simply air in between these systems. Now, if I bring the RF, the receiver end closer to the transmit end, you can see the signal level going up and up and up and up. And when I almost touch them, you can see the signal level is very much higher, right? Again, I can prove that that is the signal by turning off the power. And of course, it goes back down to minus 40. So there's my RF signal being transmitted. So at least we have kind of proof of that. Now I'm moving the RF, the waveguide away, and we see that loss, right? But it's still in the dBm kind of levels, so that's pretty good signal transmission, right? Very directional. If I move on either side of the waveguide, you won't see much change at all. If I put something in the middle of the waveguide though, or the waveguide path, so I'm going to take this copper plate and I'm going to put it in front of the waveguide. So as I put it in front, you'll see the signal almost go to 0, because now I've got this copper plate in the middle of the waveguide path, or the wave path, and so it blocks it. If I lift up the plate to move it out, you'll see the signal go back up. So hopefully that's enough to convince you that I'm actually transmitting a signal. Later I'm going to do a measurement on the waveguide wavelength here. But I want to point out a few of the other elements. So the first thing we have from this coaxial source is we have the coax to waveguide transition. So this is simply a piece of waveguide. I showed it to you in class the other day with a little probe on it. I'm going to show you a different version, but it looks similar to this. It has the probe, and that allows us to get signals in or actually out of the waveguide. This is the crystal detector probe system, but it's the same as the this unit here, which is bringing signal in. Now here I have a variable attenuator. An attenuator in waveguide is basically an element that can reduce the electric field. Primarily they work on the electric field, and of course if the electric field decreases, then the magnetic field decreases. It's going to be a little difficult to demonstrate how that attenuator works, but if you look at this picture, I'm looking straight down the waveguide, and as I turn the knob, hopefully you'll be able to see something come. Hopefully you'll be able to see that piece of metal come down into the waveguide. It's very hard to see, but there's a piece of, it's actually conductive material, and when I adjust it out of the way, then the waveguide is clear. Maybe this version will be a little bit better. But you can see that little vein coming down into the waveguide. So that is coming into the electric field area, and when I put that down, so now I've got it out, right? If I put it down into the waveguide, that is going to attenuate the electric field signal. And like I said, if you attenuate the electric field signal, you're going to attenuate the magnetic field signal. I've got one attenuator here. I've got a second attenuator here. This is a little finer adjustment. Here's the fine adjust unit here. And again, very difficult to see what's going on inside the waveguide, but there's a little vein that is turning inside, and as that turns, it attenuates the electric signal. Hopefully you can see it coming up at an angle. So it, when it's fully vertical, it's going to be attenuating the most, just like the other one did. When it goes fully horizontal, it's going to be attenuating the least. Because remember, the electric field signal is in this vertical direction, the TE10 type electric signal. All right, after the attenuators, we have a very unique element. This is a frequency meter, and it's purely mechanical. It would be too difficult for me to show you inside exactly what's going on, but inside of the piece of waveguide there's a very tiny hole, and this is called a cavity wave meter, and it actually acts as an LC circuit. And when I adjust this dial, I can adjust the frequency at which that resonates. It's actually fairly similar to this adjustment knob that we did on the slotted line, purely mechanical, right? Just to give you an idea about this, I'll dial down to my frequency of operation. I said I was operating at 8.5 gigahertz, so I'll dial this down to close to 8.5 gigahertz. 9, very unique element here. This has been replaced by frequency counters, but back in the day we could not do that. So I'll get down close to the bottom range of this waveguide operation. Remember, this is 8.2 to 12.4 gigahertz is typical. So I'm down there 85, 857, and I'm watching my meter to see if I can show you what I need to show you. So what I wanted to show you is what happens when I get to that meter location. Hopefully you're going to see a very small dip in the needle. Maybe about right there. Let me go a little more and see if there it was. See that little dip in the meter? That tells me that we are at that frequency. So what you would do is adjust it. You would come back here and you'll see that it reads almost exactly 8.5 gigahertz or 8,500 megacycles, they used to say, 8.5 gigahertz. So this system, incredibly precise piece of instrument. It's really just a mechanical micrometer type of setup. But back in the day, before we could measure high frequency signals with digital counters, we could use this to detect the frequency. The next element is our slotted line system, identical to this in operation. We have an adjustment, we can adjust the probe, and I'm going to use that to measure the wavelength a little later. And then we have our waveguide horn. Now the waveguide horn is essentially a load, right? Because it's allowing the energy to pass through. But one of the big differences in waveguide is loads are now kind of, how does the field propagate? If the field is allowed to go out, then that's like a match because there is no reflection. Previously, a match was a device like this, right? There's a 50 ohm match, right? But now in waveguide, a match means a signal that can go out and not come back. If I had a mismatch, it would be a signal that goes out and comes back. And we'll be able to show that when we put a reflective element inside of the in front of the waveguide. On the other end, like I said, we have another waveguide horn to gather the signal in, and then we have this directional coupler. These directional couplers take a little bit of that forward energy, and actually it's being terminated here, but I could measure that. It was useful in waveguides to be able to measure a little bit of the energy going forward so that you would know your system is working. And then we have our power detector on the very end. So that's a basic waveguide system. I'll stop here so that we can show that. Well, let me just show you a load first. Loads that are made as transitions are something like this, and you are not going to be able to see that. But if you were able to be in the room here, you'd see a little pyramidal cone down in the waveguide. And that's a load, that's an adjustable load on the waveguide. I happen to remember I had one of the load elements taken out a while ago. It's actually been broken. The tip is kind of broken off. But that is sitting inside the waveguide. This material, this blackish material here, is a carbon-based load resistor. So that's what a load resistor looks like in waveguide. Now you might say, why is it pointed, right? Well, remember, the wave is coming in from the left-hand side there to the load, and we don't want that wave to be reflected at all. So making a smooth transition from pointed to fat is basically absorbing a little bit more of the energy. Similar to how the horn flares out from a waveguide dimension out. So we don't want any reflection, and so this is a smooth transition. And likewise on absorption, we just want to gradually absorb it. So we have different kinds of waveguide loads. We can adjust their position. This is the same thing, only as I adjust this, I'm adjusting where the load is. This is another attenuator. This is a fixed attenuator, which has another one of those little veins in it. This one, you can see that little vein in there, mounted a little bit below the, remember the waveguide is on this side, so that attenuation is going to be in the E field direction. All right, I'll stop there, and then we'll take a few measurements. Actually, before we completely finish on that, I wanted to show you a waveguide reflection, right? So I'm going to look at my VSWR meter up there, and well, actually, I'll show you my power meter first, right? So now I'm going to stick that copper plate in front of the waveguide, right? And you're going to watch that signal go down, right? So there's signal. There's a signal being reflected, right? Now, look, I'm going to show this as I bring this copper plate closer and closer to the waveguide end, right? And so now the energy goes out, but it's reflected back. So we should be able to measure that. And so what I've shown here is I've got my probe here, and I'm going to adjust this probe back and forth, so to the right, to the left, and watch what happens to the waveguide meter. See the signal go up, and then it's going to come back down. So that is a standing wave in the waveguide. So I've moved the probe back and forth. And that's because the energy that went out was reflected back. Those two waves interfere with each other and create that VSWR pattern. We're going to use that VSWR pattern because we know between no signal and up to a peak was like the difference between a open and a short, so that's a quarter wavelength. And if we go back down to a short or no signal, right, between two no signals will be a lambda over 2. So that's how we're going to measure the waveguide wavelength. Now remember, waveguide wavelength is quite unique in waveguides because the wave is actually not traveling straight down the waveguide, but it's kind of bouncing along the waveguide, which is dependent on the waveguide size and also the frequency of operation. So we need to record the frequency, we need to know what size waveguide we have, and then we're going to measure that lambda value. In coax, we never worried about the frequency because how the signal traveled down the coax, right, did not matter. But in waveguide, the frequency will depend on the bouncing of the wave down the waveguide, which affects the measured lambda value. Not the true lambda value inside, which is related to, well, it is also affected, but it's not changing the velocity of propagation by changing the dielectric, but because of the path that the wave takes, that zigzag path down, that will adjust the measured wavelength.